So the second part of the week 2 lecture. Now I'm going to talk about the measuring of the neural activity that generates conscious experience. Okay, and as I mentioned in the beginning of the lecture, some of the papers that you'll be reviewing in the general club or presenting in tutorial 1 is going to require some knowledge of the neural activity. So the level of the neural activity knowledge is not huge to be required, but I'm going to give a very small overview of this lecture. And more involved and also the complicated issue of the neural activity is going to be covered in the subsequent lectures. So don't worry too much if you do not know about this type of the details as of yet. Okay, so as the title of this slide says, measuring neural activity in the brain is actually very, very complicated. So to start with, here's the slide that I used in week 1, that our brain is composed of this sheet of cortex, whose width or thickness is roughly 1 to 2 millimeter across all the areas of the brain. And then for each of the right hemisphere and the left hemisphere, you can imagine this 1 millimeter thickness pizza-like size of the disc on the left and right, and then crumbled like this, and then put it into your skull. That's how the cortex looks like in reality. And then within each of these 1 millimeter cortex, 1 to 2 millimeter cortex, cortex is composed of the sometimes 5, and most of the cases 1, 2, 3, 4, 5, 6 layers. And each of the layer has distinctive connectivity pattern to other areas and also within the areas. Roughly speaking, which I'm going to talk about in more details in the lecture, in the subsequent lecture, that layer 4 is usually it's a special location for the cortex, which receives the inputs from other areas of the brain. And then the input goes from layer 4 to 2, 3, and 5, 6. And then 2, 3 is usually the area that receives input from other areas. And so 5 and 6 is the 2, 3 is the one that generates some kind of processing and also receives input from area that are higher brain areas to the input area. On the other hand, 5 and 6 projects the output of neurons as a spike into areas so-called thalamus or cortex, other cortical areas. Okay, 4 is the receiving input from lower areas or thalamic areas, and then 2, 3, and 5, 6 is doing something different. That's the most important thing for now. Okay, and then this 300 micrometer numbers are depicted here is the rough size of the so-called cortical columns, and within these areas, it's like 1/3 of the 1 millimeter. The neurons within this, areas do something very similar to each other, and we will go into the detail in the next week's lecture. So as I said, important thing is that cortical layers are composed of the 6 layers, and then each of the neuron is composed of a cell body, this triangle-like shape, and the axon that usually goes into bottom. By the way, this 1 to 6 is roughly in the order of cortical surface to the axon, white matter called the location that has bundles that goes into the other cortical areas or thalamus. Okay, 1 is closer to surface, and then 5 or 6 is closer to the sort of the internal of the brain. And then the axons go out to other neurons nearby, or through the white matter to go to the other areas. And then dendrites are the ones that it goes in the other direction. Okay, and to the surface, it extends this dendrites, and that's called the apical dendrites. The main dendrite, and you see a lots of spiny things here schematically, and that's called spines. It's a contact location for the other neurons. And then the dendrite can also go into the lateral direction, and also slightly go down direction as well. Okay, and then the synapse is a part that connects one neuron to the other, and each of the synapses can be either excitatory, like exciting other neurons to fire more or spike more, or inhibitory. It means that one neuron's inhibitory input makes the receiving side of the neurons to fire much less likely. And then I already mentioned that the spiking or firing is the sort of signal communication method that each neuron uses, and spike and firing is more or less are used in an interchangeable manner. And each of the spike and firing can excite or inhibit other neurons. Okay, as I said, that so this is a sort of schematic of the brain, and as you see, the upper layer is closer to the surface of the cortex. And by the way, this is the coronal slice of the brain, as I explained the anatomical terms last week. And if you are not sure, please check the week 1 lecture slide again about coronal slice or lateral and medial and things like that. And then, as I said, that towards below layer 6 is the white matter that collects all the axons coming from this area to go to the next area. So that goes to sometimes here or sometimes there and so on. All right. So the first neuronal measure that we are going to introduce is electroencephalogram, EEG. And EEG is probably the cheapest method that I'm going to introduce. And also it's also non-invasive, meaning that it doesn't make any damage to the people or skin or skull. Okay, and here's a brain, and then you can see that each of the electrodes, as you see in this figure, is attached onto the skull of the people, and then all these leads are coming out from all the electrodes, and then that connects to the amplifier, and the machine stores the electrical activity. And then this is a schematic of the EEG electrode that sits on top of the skin, indicated by the purple layer, and then the skull, that's bones, that's indicated by this green, and then beneath that, finally, we have a cortical surface that generates the neural activity. And the resolution of EEG is, at the best, it is 1 centimeter. And that's a really bad in terms of spatial resolution of the neural activity. And then as a result of this type of the EEG recording, what you will usually see is this type of the recording over the time. By the way, I'm going to show the time scale later in the video. Here, this CZ means the location of the electrode in the brain or the skull. CZ is usually at the top of the skull around here. And then you will see the range of the response varies 150 microvolts, but it depends on the resistance of the electrodes. And the highly related measurement is the magnetoencephalography, called MEG. The EEG electroencephalography measures the electrical signal, but the MEG measures the signal that is magnetic. And here's the MEG machine. And within Melbourne, there is one machine in the Swinburne University. And we collaborate with the people over there to measure this magnetoencephalography. And magnetoencephalography's advantage is that unlike electrical activity, magnetic fields is going in a slightly different direction, orthogonal direction to the EEG. And it's less affected compared to EEG by the skull and also skin. So in the end, what you'll see is that the signals from MEG can measure the activity in the deep in the brain and more corresponding to the direct recording from the inside of the brain, intracranial EEG as I show here. And this is a time scale of measurement 1 second. And so you can see MEG is quite good in terms of the temporal resolution as well as the spatial resolution to some extent. And this little bit of gross bloody image is the intracranial recording situation. So intracranial recording is most usefully used in the clinical settings. And I have lots of collaboration with these type of neurosurgeons who implant all these electrodes to monitor the location of the origin for epileptic seizures. As we will also cover in the subsequent lecture, epilepsy is sort of the uncontrolled, burst of electrical activity in the brain, and that generates sometimes loss of the memory, sometimes loss of the percept, but yeah, sometimes even loss of consciousness can accompany with this epileptic seizure. And for some unfortunate population of people, epilepsy cannot be treated by just having a drugs. And in that case, all these people and the surgeon resort to this, surgery to remove the source of the epileptic seizure. And for that matter, you first need to implant the electrodes into the brain. And if you do that on the surface, that can record this activity called ElectroCorticoGraphy, and sometimes called the ECOG. And then here, as you see, from the surface, you can directly record the electrical activity, unlike EEG, which is filtered through the skull and also scalp, skin and bone, right? But ECOG directly records the activity on the surface of the brain, and therefore it has a really good signal-to-noise ratio. Other type of the intracranial recording corresponds to this so-called depth recording. Unlike surface, sometimes people put the electrode inside, which is potentially more invasive, but in reality, ECOG is more invasive due to the possibility, more likely infection, possibility. And here, you don't need to open the skull. This particular figure is opening the skull, but you can drill the hole here and then put the electrodes, depth electrode recording like this. And this is one schematic figure or potential actual recording from the people with epileptic, seizure and also implantation of the electrodes. And this particular figure is reported in this Buzaki, who is a very famous, neuro scientist, in this, where the patients were recorded with the ECOG electrode on the surface, as well as a depth electrode inside of the skull, inside of the brain, as well as the scalp electrode, on the surface. And as you can see, here, O2, OZ is back of the brain, and if Z is the front of the brain. If the EEG electrodes are separated like this, much of the distance, you'll see completely different, activity. So meaning that the EEG has a spatial resolution above, several centimeters. But underneath OZ, if you have an electrode implanted, then you'll see quite a bit of the different kind of signals. But on the surface of the ECOG and also depth of the LFP, you will see more or less the correspondence as long as the recording location is close enough. if you can record the ECOG from the surface of the cortex like here, and then LFP again inside of the brain, just beneath the ECOG, then you will start to see a correspondence in terms of the opposite polarity between the ECOG and the LFP. And there is some difference in terms of collection of voltage, because electrical activity always decays as a function of the distance. The ECOG or LFP always reflects the neuronal activity that is closest to the electrode more significantly. And then this particular experiment succeeded to record the neural activity from inside of the cell, and that's called intracellular recording. And here, I think this is actually coming from the animals. Then you can see this type of the vertical, sharp, voltage fluctuation from inside of the brain, inside of the neuron. And this is what I have been calling as a spikes, okay? So when the neuron collects enough input signals, then that starts to generate this type of a spike activity, okay? And then here, the fluctuation of this intercellular membrane that doesn't generate spikes reflects the input into the neuron, which is still below the threshold for the spikes. So you'll see there's lots of spikes here, followed by reduction of the membrane potential, during which it doesn't fire at all. And then that's correlated with this large fluctuation in the LFP and the ECOG. And you'll see that lots of firing of this particular neuron was also correlated with the LFP inside and also ECOG outside of the cortex. And what it means is that when neuron tends to fire a lot like this, it tends to be the collective firing across many, many neurons. And that can be detected both by LFP as well as ECOG. However, as you can see that both ECOG and LFP is not sensitive enough to pick up each of the neurons firing. Around here, it's a bit hard to see whether a neuron is firing at this time or not, or this time or not. But when there is a collective action, you can see it over there. And then sometimes there is a dissociation. Many neurons are firing here, and that's detected by LFP and the ECOG, but this particular neuron does not. And that the relationship between these single neuron firing and the conscious experience is the one that we will be discussing in the next few weeks. And that's we will talk about more about local field potential fMRI EEG in the next video.